All right, welcome to Waka Breaking It Down. Today we will be continuing our exploration of exponential equations. We're looking at things like growth and decay today, right? And to do so, we will be using this particular activity. This is it says class 47, but exponential function applications, right? This is not the introduction. So if you don't have any clue what I'm talking about, you should go watch the introductory video first and then come to this one. So our premise is that we have some bacteria that we're starting with. And you can see here down here on the chart, it says at time period 0, we have one bacteria. And then after another 20-minute period, we have two bacteria. And then you can see it doubles to 4 and then 8, 16, 32, 64. So it tells us that it's doubling every time, right? So that's our table. And then you can see that the equation we end up with matches. So the number of bacteria we're going to have, the number of bacteria is equal to what we started with, which was just 1 at time 0, right? This is time 0, 1. And then what's the rate? So what are we multiplying by every time? Well, we're multiplying by 2, so that's why you see a 2 there in that equation. So it's all represented here. When you see the 0, this is the A value. And then you're also looking for what do you multiply by, and that will become your B value, right? This 2 that we have in there. We've seen this last time. Okay, so it should be nothing new yet. All right, so then they say, well, what if you started with 25 bacteria instead of, like it's a different type of bacteria or something. Start with 25 and it doubles, right? Then that's what's going to be. Huh? There are 20. Yeah, doubling. Now, this case is doubling every hour. And one thing I need to really point out right now, which is really, really important, is this X now. What does this represent? It has to match, like the units and the idea of it has to match what your rate is. So what I mean by that is this these bacteria are doubling, but when are they doubling? Well, they're not doubling every hour, they're doubling every 20 minutes. So if I want to go for 40 minutes, then this X value isn't going to be 40, it's going to be 2, because over 40 minutes, right, it took two 20-minute periods to get to 40 minutes. So you see up here, these, even though these go 0, 1, 2, 3, these represent 20-minute periods. So in my equation, I'm not going to put in 20 minutes or 30 minutes or 40 minutes. I'm going to put in 1, 2, 3, 4, but that's going to represent how many minutes, right, for each one. So after 3 periods, if you will, after 3 time periods, right, how long did that take? Well, it took 20 minutes each one. So this is like 20, 40, this is like an hour, right? 60 minutes. So 3 time periods is an hour. So if I said, how many bacteria left over after 2 hours? Well, you wouldn't put 2 into here, right? Which is really tempting, and a lot of people mess that up on their tests and stuff. You don't put 2 in there. You put in how many 20-minute periods there were in 2 hours. Well, in 2 hours, that's 6 different 20-minute periods, right? 6 different blocks of 20. So I would be putting 6 into my equation, right? 2 to the 6th power. Well, let's see here. 2 times 2, 4, 8, 16, 32, and 64, right? So that would be 1 times 64, which is 64. All right. But the main thing is this exponent unit, whatever it is, like time periods of 20 minutes or whatever it represents, has to match what the rate is. So if you put a doubling every 20 minutes, then you better be putting in how many 20-minute blocks you're talking about. So when we look down here, now this one's a little different because we're starting with 25 bacteria and we're doubling again, but this time we're doing it every hour. So the number you're putting in there is based on hours. So it still looks like X, but it's different now, right? It's a different problem. It's a different X. You can see they even say here, this is X hours. And up here they say, this is X 20-minute periods, right? They're different. They're different. So you got to really pay attention to that and keep that straight. That's the biggest problem that students have. So watch that. All right, so starting amount is in there. Our rate is in there. This x value matches the rate. So this is doubling. It's times 2 every hour. So x represents the number of hours. Okay, so what would it mean if x was negative? Well, it's hours, so if x was negative, that's negative hours, right? So if you have b to the negative 2, that would be like 2 hours ago, right? And you can do that. Just put in a negative number. 2 to the negative 2, that's the same thing as 1 over 2 to the positive 2, because you can flip it over and change the sign, right? So that's like 1/4. It's just a quarter. So this represents a quarter. And then 25 divided by 4, so 25 times a quarter is 6 1/4, right? You just half and half again. So 2 hours before you started, there was 6.25 bacteria in there. Now, of course, you can't really have 6 1/4 bacteria. That's okay. We just report the number anyway, write it down. And then after that, you can kind of make some more sense of it and say, well, so that means it's probably about 6, maybe 7 bacteria is what I used to have, right? Because you can't have a quarter of a bacteria. It would die. Okay, new problem. We got insulin. Like my dad. My dad has diabetes. He took insulin for his whole life pretty much, right? So he's taken insulin. He puts it in. He really monitors it every day, right? And he has to watch how many his blood sugar levels and everything, right? And there's tons of people who have to take insulin. So anyway, we got a whole bunch of people. They're talking about some background to it. So in 5 to 10% of the cases, the body is unable to produce insulin, which is kind of like my dad. So he needs to take insulin. All right, so we have time entering the bloodstream in minutes. So this is now minutes. That's the first thing I'm looking for. There's like, okay, what are my units, right? What are we talking about here? So this is how many minutes? 3 minutes, 6 minutes, 9 minutes, right? So units of insulin remaining in the bloodstream. So this is the actual insulin in the bloodstream that they're watching, okay? So what do we want to model this with? Well, it should be exponential. It looks like there's some kind of multiplier going on. This says use your TI Inspire, right? So we've done this in the previous video. You just go and get a spreadsheet and put these numbers in the spreadsheet. Make sure you label the headers something. Graph it out, right? So we did something like this before, right? Get a spreadsheet, put in your headers, put in your numbers, and then insert a data and statistics page. So you have to go plus page. Put your X value in, put your Y value or Y topic, right? You got to put in what is it, like what's your X and what's your Y. You got to put those in. So you just click on those and it'll come up and you can put in what you need. And then it'll graph it out. And then you can go to analyze, regression, and exponential here, right? And then you can get your equation out of it. This is for a different problem from the intro one, right? Okay, so if you do that, you should get this equation. You should get this equation. Right? So, and you just have to write it down and just look at it. And then we're going to use that, right, to do some different stuff. So what's the initial? So 10.29 is the initial amount. 0.95 is your rate, right? 95% is left over. Basically, you're removing 5% every time. So that's what's going on, right? So that's what you want to talk about. But this is each minute, remember? So you want to make sure that context is in there. All right, and then we're using that kind of idea, that equation, to try some problems. So what about after 1.5 minutes? 10 thirds, that's the same thing as 3 1/3 minutes. That's the same thing. So you're just putting those in, right? And getting some context to it. If they ask you to solve for the time, this is like I showed you on the intro video, you need to be able to graph this. So you're going to graph this piece, and then you're going to graph this piece, and then you're going to look for where they intersect. We did this back in the quadratic unit, so maybe you have to remind yourself how to use the calculator and find an intersection. Okay, when you do that, you're going to find out that x value is 31.9. And again, it's in minutes, right? Because we were talking about 95% remaining after every minute. Okay, now we're talking about half-life. They say let's look at half-life. So when they say half-life, there's kind of a couple different ways to think about it. Sometimes we make our rate 1/2 to match that idea, but in this case, we already have an equation. We already know the rate is 95% per minute. So we're asking ourselves, how many minutes does it take to get half of what I started with? So I started with 10, so half of that would be 5, right? So I'm just going to graph this like I already have the graph because from the previous problem, right? But now I'm going to graph 5 and say, where does this equation equal 5? And look for that intersection. And you should get 13.5 out of it, right? You just need to be able to pop that in your calculator and use your tools, your menu, and analyze to go find the intersection. I'm glazing through it because we've done this before, so it shouldn't be something new. All right. Yeah, it doesn't matter what you start with. The decay rate should be the same. That's never going to change. The half-life, if we start with 15 and we try to do half of that, how long would it take for that? Oh, that's also 13 and a half minutes. So it doesn't matter what you start with. You're always going to get half of that after 13 and a half minutes in this case because the percentage didn't change, right? It's the percentage that will affect how long it takes for something to decay a certain amount, right? A certain percentage. Okay, so one thing about exponential equations, when you graph them out, it'll never reach zero. So if you think about it, it's like, okay, I've started with 100 things, and half of that is 50, and half of that is 25, and half of that is 12 and a half, and half of that is 6 and a quarter, and half. If you keep halving, you're always going to have something remaining, right? There's going to be a little bit left over. And even if you take half of that, you're still going to have a little bit left over, right? So you never, ever get all the way to zero. So you're going to notice on exponential equations, they'll come down and it'll get really, really close to the x-axis, but it's never going to quite touch. It'll get really, really close. So it's kind of like an asymptote, right? That x-axis is an asymptote. All right, so keep that in mind. And there's another one here. I think I'm going to stop the video there because that's just probably enough information, like knowing how to use the calculator, knowing that you're supposed to graph something to find an intersection, or just plugging in a number to find your value. And also really paying attention to the units, right? What is the exponent units and the rate units, and really thinking about those, right? When you're doing these problems. Okay, so you can just see you're working through a few things here. These answers are posted, so make sure you take a look and practice, right? It's just another practice problem. You got a couple of those. You can see that we're doing some more intersections and looking for that. Okay, and yeah, just a few problems to practice, right? But it's all the same idea, same idea. Either you're growing or decaying. All right, I think that's enough information. And like I said, the most important thing is this power thing. And you can see right here that this is getting a little different too, where you have to kind of adjust your exponent a little bit. So that's the part you really got to pay attention to when you're going through these problems. Okay. All right, that's it. That's the part there. All right.